Today's lecture, we're going to look at the periodic table and we're going to get into the mole. So we still have Chapter 1 and Chapter 2 homework due this Sunday, May 24th at midnight. We're going to finish Chapter 2 today, and on Sunday I will have a review session 8 to 9 p.m. in Blackboard Collaborate if you have any last-minute questions with your homework. I'll be there to help. Isotopes are elements with the same number of protons but a different number of neutrons. Remember, our atomic number is our number of protons, and so carbon, for example, is atomic number 6, and so we can see in all of these isotopes of carbon, I have 6 protons. Because it's a neutral atom, I have the same number of protons and electrons, because my protons are positively charged, my electrons are negatively charged. Where these isotopes differ, however, are the number of neutrons. And so here are 4 isotopes of carbon: carbon 11, carbon 12, carbon 13, and carbon 14. So the atomic number stays the same. The atomic number 6 for 6 protons. What changes is the mass number. We can see I've got carbon mass number 11, 12, 13, and 14. The mass number changes because the number of neutrons changes. Right, I've got 1 AMU approximately for each proton and each neutron. So for carbon 11, I have 6 protons and I have 5 neutrons. 6 plus 5 is 11. So we can see for carbon 12, I've got 6 and 6. And then for carbon 13, I'm adding in 1 more neutron for each of those isotopes. So isotopes are elements with the same number of protons, right? So it makes it an atom of carbon, but a different number of neutrons. That's making it an isotope of carbon. Remember, you cannot change the number of protons. If you change that number, you're changing the atomic number and you're changing the element. So here's an example of that. We've got 4 different atoms, atom A, B, C, and D, with our number of protons and our number of neutrons. Which atom is an isotope of atom A? So atom A has 18 protons. Well, isotopes have the same number of protons but differ in their number of neutrons. So atom C also has 18 protons. So that must be an isotope of atom A. Now for the next question, which atom has the same mass number as atom A? So remember, our mass number is determined by adding our number of protons and our neutrons together. So for atom A, 18 protons, 19 neutrons gives me a mass of 37. For atom B, I would have 35. And for atom C is 36, and D would be 37. So which atom has the same mass number as atom A? We see that both atom A and atom D have the same mass number of 37 AMU. They are not isotopes of each other. They are actually different atoms, different elements, as we can see based on the number of protons. But they end up, based on the difference in the number of neutrons, they end up having the same atomic mass. This is actually very common in chemistry, that there are elements that have different isotopes with different abundances. For example, one common one is chlorine. There's chlorine 35 and chlorine 37. Because it's chlorine, we have the same number of protons, 17 protons, but as you can see, the mass number differs for both of these, chlorine 35 and chlorine 37. So where that difference comes in is the number of protons. We could see that we have approximately 18 neutrons here, whereas we have 20 neutrons in this isotope, just based on the difference in the mass numbers. So this is actually an important aspect of this isotopic distribution and the patterning you can see in a molecule if it has an atom like chlorine attached to it, because chlorine exists in different isotopes with known abundances. So in a typical sample, about 75% of the sample weighs chlorine 35, and about 24% of the sample is chlorine 37. So it gives you this really unique pattern if you were going to look at the weight distribution of that sample, where you would see 75% of the sample weighs this much and 25% of the sample weighs 2 AMU more. So it gives you this shouldering pattern that's very distinctive of that isotope. But how do we use this, right? How do we use this information? And fractional abundance helps us determine basically what mass I should use for that sample, right? Because I'm looking at that chlorine example. I've got chlorine 35, chlorine 37. When I go and use chlorine in a reaction, what weight should I use to figure out how much chlorine I need? Because that chlorine 35 and chlorine 37 is mixed together. It's the same thing with boron. Here's another isotope. There's boron 10 and boron 11. Boron 10 has a weight of about 10 AMU and represents about 20% of all boron. Boron 11 weighs 11 AMU and represents about 80% of all boron. So again, I want to use boron in a reaction. I want to know how much to use, but they have a different weight and they're mixed together in one sample. So what weight should I use? Well, we're going to use the fractional abundance to determine what is the average weight of this sample. And that's the atomic weight that we're going to use. The atomic weight is the average mass of an element where you take into consideration that fractional abundance. How much of each isotope do you have available in that sample? So boron, for example, the boron 10 at 10 AMU, that was about 20% of the sample, and the boron 11 weighed 11 AMU, and that was about 80% of the sample. So what you can do with that information to determine what is the average atomic weight that we should use for that sample, you'd say, well, boron 10 weighs in at 10.103 AMU, and as a decimal, right, is 0.1978 of the sample. And boron 11, right, we can take a weighted average of the sample. Boron 11 is 11.009 AMU, and that represents about 0.822 of the sample. So by multiplying those together, we can do a weighted average of what is the atomic mass that I should use for boron, given that it consists of two isotopes in two different amounts. And so if I multiply 10.013 AMU by 0.1978, I see that the weight contribution from boron 10 is approximately 1.9806 AMU. Do the same calculation for boron 11 and I get a weight contribution of 0.88314 AMU. So I'm going to add those two together now to get the overall weighted average of this sample of approximately 10.8120 AMU. Now for my significant figures, I look and see in this measurement I have 5 significant figures, and in this measurement I have 4 significant figures. So that means after I multiply, I should report to 4 significant figures for the answer. So moving down the line, I would have 4 significant figures right here. And the same for this number, 4 significant figures. So now I do the addition. I've got 3 decimal places in that number. I should report the final answer to 3 decimal places. So 8.12 AMU. And a question you should ask yourself is, does this number make sense? Does this number make sense based on the information we have? And the answer is yes. This number makes sense because I have boron 10, that's 20% of the sample. I have boron 11, that's 80% of the sample. So yes, I would expect the final answer to have a weight that is closer to boron 11, right? The weight is 10.8, that's much closer to 11. So that answer makes sense, right? It's headed in the right direction because the average ended up being 10.8 when we know 80% of the sample weighs 11 AMU. So here's a question for you. We are running a reaction. We discover we make a new element. You obtain a sample of that element and you determine it's made of two isotopes, isotope X23 and isotope X25. To help calculate the atomic mass, you determine the ratio of the two isotopes. You find out that the gold spheres are X23 and they weigh 23.02 AMU, and the blue spheres are X25 with a mass of 25.147 AMU. What is the atomic mass of element X? And so the first thing we want to do is we want to figure out the percentage of each of those samples. And we'll look and we'll see that we have 20 atoms represented in this sample. And of those 20, I have 5 that are the gold spheres, and I have 15 that are the blue spheres. So gold ends up being 5 out of 20, right, or approximately 25% of the sample, and the blue spheres end up being 15 out of 20, or 75% of the sample. Now we can determine the atomic mass for this element. Right, gold is X25, and that weighs 23.02 AMU, and it represents 0.25 of the sample. We want to use this as a decimal, not as a percentage. For the blue sample, that weighs 25.147 AMU, and that represents 0.75 of the sample. So we multiply those together. I get a weight contribution from the gold spheres of 5.755 AMU. And I get a contribution from the blue spheres of 18.86025 AMU. And just like the last time, now I've got a weight contribution from both of those isotopes. I want to add that together to get what is the overall atomic mass of this sample. Adding those together, I get approximately 24.61525 AMU. Now we need to take a look at our significant figures and see that I have 4 significant figures in our measurement of atomic mass. The percentage came from a counted number, so we're going to say that's an exact amount. We counted how many gold spheres we had and how many blue spheres we had. So 4 significant figures in my measurement. I should report 4 significant figures in the answer. And then beyond that, I have 5 here, which would give me 5 here, which would give me 3 decimal places I should report in the final answer. So we should say the atomic mass would be about 24.615 AMU for this sample. When we're looking at questions like that, you'd like to think that those isotopic distributions are fixed. However, they are not, and that's a good thing. It actually is interesting that isotopic distribution varies throughout the world. And there's this hypothesis called the "you are where you eat" hypothesis that basically looks at the isotopic distribution in your bones and your teeth and your hair as a product of where you grew up and where was the food grown that you ate, and the water that you drank, where was that from? Because as we can see in these two maps show isotopic distributions of hydrogen and deuterium and oxygen, the oxygen 16 versus oxygen 18. So you can see in these maps that the distribution, even within the US, is drastically different for those isotopes. And so we can do that isotopic analysis in forensic science to help determine where a sample might be from based on the isotopic distributions. Ways that's used within the forensic science community, for example, if you have a missing person or if you have a skeleton that you found, you can do isotopic analysis on the bones to check out the isotopic ratio to get an idea of where could this person be from based on the different isotopes in the bones. Another example that this is used in nitrogen, for example, nitrogen is found in cocaine. You can use that isotopic distribution in nitrogen within an example of cocaine to help determine where in the world that plant was grown. So there are some interesting ways these isotopic variations are used throughout the world to determine where someone was born, someone lived, or something was grown or made. That can be used to help authenticate a sample or help determine, location of where it was created. Another way that this is used, the carbon-12 analysis versus carbon-13 analysis is done in looking at truffle. Truffle oil is commonly faked and it's not an actual product of truffles. Well, we can actually do a carbon-12 versus carbon-13 analysis to determine, is that authentic truffle oil that was grown, or was it an artificially produced product that was made by just mixing chemicals together that would give you the taste or the flavoring of truffles?